Hello everyone. I am Himanshu Mishra, and I am the PhD research scholar in the Department of Applied Mechanics, IIT Madras. Last week I have discussed some questions related to the radiation heat transfer. We have solved some problems which are related to the shape factors, view factors, and how the radiation heat transfer take place at when we place the surface at different orientations. And we found that the surfaces at different orientations have a different radiation heat transfer, which entirely depend on the direction in which the radiation is going to emit from the surface and reaching to the other surface. So this week we will be solving some problems related to the multimode of heat transfer, which contain radiation heat transfer as well as some convection part of it. We will be solving some multi-plate heat transfer in which we put some plate between the plate in the systems, and we will see how the radiation heat transfer will affect. So let's begin with the first question. So this is a question that I actually include in the previous week, but could not able to cover. So let's start with the same question. So in the question number first, there are two subparallel plates with diffuse gray surface, and we have given the temperature of the two surface plates. We have given the emissivity of the two surface plate, and we need to determine the irradiation and radiosity of the upper plate. We also need to determine the radiosity of the lower plate and the net radiation exchange between the plate per unit area. So let's start with the first question. So we have a two plates here. This is T1, which have the temperature of 1000 Kelvin and emissivity of 1, and this is K2 having the temperature of 500 Kelvin and emissivity of 0.8. Now there will be some radiation from the top surface. It will reach to the bottom surface and it will reflect back. And there will be some radiation from the bottom surface also. So this reflective radiation is ρ2 EB1, and the emissivity from the bottom surface is defined as epsilon2 EB2. First, we need to determine the irradiation to the upper plate. So the irradiation to the upper plate actually contains the flux emitted by the surface 2 as well as the reflex flux emitted by the surface 1. So it will be radiation which is coming out from the surface 2 as well as the reflection so it can be written as so here I'm writing ρ2 as 1 minus epsilon2. So we just need to put the values here. So epsilon2 is 0.8, and we know the Stefan Boltzmann constant, and temperature T2 is 500 Kelvin, whereas temperature T1 is 1000 Kelvin. So first we just need to calculate the magnitude here, and it will come out about 14.175 kilowatt per meter square. Now we need to determine the radiosity for the surface one. So radiosity is the radiation component which is coming, total radiation which is coming out from the particular surface. So the radiosity from the top surface is the radiation which is coming out from the top surface. So radiosity of top surface is given by since the top surface is a black body, it has the emissivity 1. There will be no reflection from the top surface. So we will write emissive radiation. So the radiosity actually contains the emissive part as well as the reflective part. Since we have a black body, so there will be no reflective part, and the radiosity will contain entirely of emissive part. So we can just calculate directly by putting the values. And the radiosity will be around 56.7 kilowatt per meter square. Now we have calculated the radiosity from the top surface. Now to calculate the radiosity from the bottom surface. Since the bottom surface is not a black body, it will have a reflective as well as the emissive part. So for the bottom surface, it will have this emissive part as well as this reflective part, which is we already calculated 14.175 kilowatt per meter square. So basically this radiosity of the bottom part is equal to the irradiation of the first plate. Now we also need to calculate the net radiation exchange between the plates per unit area. So the net radiation exchange will be given as we need to put the we need to substitute the value here. And we can find the net radiation exchange 42.525 kilowatt per meter square. Now there is other way we can find this. We can also find the net exchange of radiation as radiosity minus irradiation. So we have calculated the radiosity, which is 56.7, and the irradiation is 14.175, which will give the same answer. So in this question, we have given the two surfaces, and we have given the temperature and the emissivity of the two surfaces. So one of the surface is the black surface, and we need to find the irradiation radiosity of both the surfaces, and in the end we need to find the net exchange of radiation. So for the radiosity, we need to keep in mind that radiosity is defined as the radiation which is going out from the surface. So it can be happen in two ways. First, there is a emission from the surface, and second, there is a radiation which is coming out from the other surface, which reflect at the surface at our specific surface, and after reflection there will be some net outgoing of the radiation. So there will be emission of the radiation as well as the reflection of the radiation. So in that way, the both the radiation can both the radiation are the outgoing radiation. So this is the radiosity. But for the black body, there is only one way by which the radiation can be outgoing radiation, and that is the emissive. The black body can emit all the radiation and it can absorb all the radiation. So there is no reflective part from the black body. So to find the radiosity from the black body, there will be only emissive component of the radiation. And if the body is not the black body, then to find the radiosity, there will be emissive part as well as the reflective part. So let's move to the different next question. So in this question, we have given a long thin walled horizontal tube of 100 mm in diameter, maintained at 120 degrees Celsius by the passage of steam through its interior. The radiation shield is installed around the tube, providing an air gap of 10 mm between the tube and shield, and reaches a surface temperature of 35 degrees Celsius. The tube and shield are diffuse gray surface which with emissivity is 0.8 and 0.1. What is the radiant heat transfer from the tube? So this is a pretty standard problem. So we have given a tube which is enclosed by some other tube. So the inner one is having the temperature of 120 degrees Celsius and outer one having the temperature of 35 degrees Celsius. And the inner one having the emissivity of 0.8 and outer one having the emissivity of 0.1. And we need to determine the radiant heat transfer. So there is a standard relation for that. So we know the standard relation between two parallel plates, two parallel cylinders and all. So these are the cylinders. There is one cylinder inside the outer cylinder. So the configuration is actually of a two parallel cylinders. So we know the heat transfer relation due to radiation. This is 1 and this is 2. And the overall heat transfer is actually given by so all the radiation from surface 1 will reach to surface 2. And from the previous week, we know that if all the radiation from one surface reaches to the other surface, then the view factor will be 1. So in this case, the view factor F12 will be 1. And now we just need to substitute the value. So we need to find the total heat transfer per unit length. So we need to find this. So just put the values here, and I'm writing the temperature in Kelvin. So in such radiation heat transfer, make sure that to write the temperature in Kelvin. Always use temperature in the Kelvin here. And epsilon 2 is 0.1. And by just calculating this, it's just a calculation, basic calculation, and we will get the heat transfer per unit length as 30.2 watt per meter. So this is pretty standard problem where we have given two parallel configuration of the cylinder, and we need to find the heat transfer from the inner cylinder to the outer cylinder. And in such cases, we know that the view factor is 1. That means all the radiation from the inner cylinder will go to the outer cylinder, and therefore the view factor from the inner cylinder will be 1, which is given by F12 equals to 1. And then the relation is pretty standard in such cases, because we know the heat transfer radiation in case of parallel plates, parallel cylinder, and we just need to substitute the value to find the heat transfer per unit length. So let's move to the next question. So in the next question, there are two concentric spheres of diameter d1 and d2 separated by air space and have surrounded temperature of T1 and T2. So if the surface are black, what is the net rate of radiation heat transfer between the spheres? And the next part is, what is the net rate of radiation exchange between the surface if they are gray, having the emissivity of epsilon 1.5 and 0.05 epsilon 2? And then what is the net rate of radiation exchange if D2 is increased to 20 meter and emissivity are the same, and D1 is 0.8 meter? What error would be introduced by assuming black body behavior of the outer surface emissivity of 1 with all the other conditions remaining the same? So again, this is pretty standard problem. So in the previous one, we have a two parallel cylinders, and in this problem we have a two parallel sphere. So we have inner sphere and we have the outer sphere. So again, we know that from the configuration itself that the radiation from the inner sphere coming out from the inner sphere will incident on the outer sphere. So all the radiation will incident on the outer sphere, and therefore the view factor F12 will be 1. So here 1 is my inner and 2 is my outer sphere. And if I want to make a network diagram, so this is my network diagram in this case, which is similar in the previous question also. So in the previous question also, this network diagram will be similar. So here, this is the emission from the surface 1, and this is the radiosity from the surface 1. So if we use a standard heat transfer relation, which is the temperature difference divided by the total resistance, so we can directly use these thing as a resistance here. From the network diagram, we can use the temperature difference and the total resistance for calculating the heat transfer, and the total resistance are given by summation of these resistance. So for the first part, we have given that both the surfaces are having the black body surfaces. So the emissivity in both the surfaces are 1. So we know that for the black body case, the heat transfer will be given by this. And you can also verify by putting the emissivity 1 of both the surfaces in this relation. So in the previous question, we have used this relation. We use this resistance to find the heat transfer, and if you put emissivity 1, you may get this relation here. So we just need to put the values. And we already know that F12 is 1. So just calculating these quantities, we will get the net radiation heat transfer is 1995 watt for the black body case. These are the black surfaces, where my surface 1 and 2 are the black surfaces. So that means the emissivity is 1 Now, in the second part of the question, we have given the surfaces are diffusive as well as the gray surfaces, and we have given the emissivity of both surfaces. So from the network diagram here, which I have shown here, we can write down the same heat transfer relation. So I can, this is my total resistance. So the resistance from the network diagram, I can write down the total resistances. So this is my expression. This is the same expression we have used earlier for the previous question. So the only difference is the area. So here we have to consider the area of the sphere, surface area of the sphere, and in the previous question we have actually considered the surface area of the cylinder, because in the previous question we actually calculate the net radiation heat transfer of the cylinder, and in this case we are doing for the spheres. So I can simplify this expression further as, so I just put the area expression for the spheres and just simplify the relation. So this is my relation which come from here only. I just put the expression of area here and simplify it. So when I put the values, so just calculating this, we will get the heat transfer as 191 watt. So for the black body case, we got 1995 watt. And for the gray diffusive surface, which with specific emissivity, we got the heat transfer as 191 watt. Now in the next part of the question, it is given that if the diameter of the outer surface increased to 20 meter, then what will be the heat transfer? So in that case, the same expression here. We will be using the same expression here, and only the diameter D2 will change. So here R2 become 10 meter. That is the only change, and all the parameters are same. So again I am putting the values. So here I am put the values. 0.4 is the radius of the inner sphere, and 20 is the diameter of the outer sphere, which is 10 meter radius. And again, just calculating it, we will have the heat transfer 983. So previously we got 191 with the diameter of 1.2 meter, and with the diameter of 20 meter of outer sphere, we got the heat transfer, net radiation heat transfer 983 watt. Now we need to calculate the heat transfer when the outer sphere become the black surface. That means the emissivity of outer sphere become 1, and the emissivity of the inner sphere remains same, which is 0.5. So in that case, we will using the same expression here, And here we put the emissivity epsilon E2 as 1. So this will become 0 because we have 1 minus epsilon 2. So it will be 0 here. And my heat transfer relation will become so this will be my heat transfer relation because this factor will be 0. So only this 1 minus epsilon 1 will be remain. So again, just putting the values here. Just by calculating here, we will get the heat transfer as 988 watt. So this will be my heat transfer, and the outer surface is the black surface having the emissivity 1 and the inner surface having the emissivity of 0.5. So in this question is a pretty standard question where we have given the two parallel spherical surfaces. We have given a temperature and we have given the several conditions. So the first condition is when both surfaces are the black surfaces. In that case, the emissivity is 1 for the both surfaces, and it is easy to calculate the radiation heat transfer between these surfaces. Now, in the second condition, if the surfaces are diffuse and gray, in that case, the emissivity will not be 1, and there will be some specific emissivity we have given for the both surfaces. And in the third case, the diameter changes, and also the emissivity is changing in the question for the second surfaces. And in all these conditions, we have used the same relations, and we just keep changing the radius and the emissivity in the same relation for all conditions here. So moving to the next question. So in this question, a cryogenic fluid flow through a long tube of 20 mm diameter, outer surface which is diffusive and gray, having the emissivity of 0.02 and the temperature of 77 Kelvin. This tube is concentric with large tube of 50 mm diameter, and the inner surface which is diffusive and gray, having the emissivity of 0.05 and temperature 300 Kelvin. Now the space between surfaces is evacuated. Calculate the heat gain by cryogenic fluid per unit length of tube. If a thin radiation shield of 35 mm diameter and emissivity is inserted midway between the inner and outer surfaces, calculated the change in heat gain per unit length of the tube. So for the first part, we have a concentric cylindrical tube which is similar to the question of previous question, and the question number 2 and 3. So the inner tube has the temperature of 77 Kelvin, and outer tube has the temperature of 300 Kelvin. So it is given in the question that the space between the surfaces 1 and 2 is evacuated. There is no air between the surfaces, so there is no chance of convective heat transfer will take place. So all the heat transfer will take place by radiation mode only, and there will be no convection heat transfer mode which is present here. So this is the condition without shield. So I already made the network diagram in this case in the previous question. This is my network diagram. So in the previous question we have solved for the two parallel spherical surfaces. Now we are doing for the two parallel cylindrical surfaces. And in question number two, we have already done that actually. So we have used a relation here for the two parallel cylindrical surfaces. So we will be using the same relation here. So for the two parallel spherical case, we use the same relation. We simplify the same relation here based on the surface area. So using the same relation, we can find the heat transfer. So the heat transfer per unit length will be given by, we just need to put the values here. So since it is per unit length, so the length will be cancelled here. So only the diameter will be remaining. So 1 minus epsilon 0.05. The diameter is 0.02 and 0.05 here. So the heat transfer will be, just by calculating, is 0.5 watt per meter. So the minus sign appearing because the heat transfer is other way around. It is from the surface 2 to the surface 1. Now it is given that there is a shield now between the two cylindrical surfaces. So this is my surface 1 and this is my surface 2, let's say. And now there is a shield, surface 3. So to determine the heat transfer in this case, we need to determine the resistance from the network diagram. So the network diagram is given as here. So this is my emission from the surface 1 and this is my radiosity of the surface 1. This is my radiosity exchange between the surface 3 and 1. And this is my emission from the surface 3. And this is the radiosity exchange between surface 3 and 2. This is the radiosity from the surface 2 and emission from the surface 2. So these are the resistance for the emission case, and these are the resistance expression for the radiosity. So now we have all the resistance from the surface 1, 2, 3 by emission as well as the radiosity. So first the heat transfer will be given as total resistance. So this is my total heat transfer relation from the total resistance, and my total resistance will be summation of all these resistance component. So this is by putting the values here of emissivity 1, 2, 3 and the geometric properties, the dimension of diameter and length. Just by putting the values, we will get the resistance as 1817 by length. So this is my total resistance here. So we got the resistance here, total resistance here. So we will be using this expression to find the total heat transfer. So I'm just putting the values here. So I'm finding the heat transfer per length. So my heat transfer per length will be 0.25 watt per meter. So now we need to find the gain in the heat transfer. So without shield, we found the heat transfer is 0.5, and with shield, the heat transfer is 0.25. So the gain or loss of heat transfer is so this is my heat transfer with shield, and this is my heat transfer without shield. I'm multiplying by 100 to find the percentage here. Sorry, this is my heat transfer with. So it will be 50% loss. So we can see directly from here 0.25 and 0.5 here. So when we introduce the shield between the two cylindrical surfaces, there will be the loss of heat transfer by 50%. So in this question, we have given two parallel cylindrical surfaces here, and we need to find the heat transfer between these two surfaces, and we know how to do it. In the second question, it is given that there is a shield with some specific emissivity of 0.02, which is inserted between the two surfaces, and we need to find the heat transfer and the gain or loss of heat transfer from it. So let's move to the different question here. So in this one, there is an opaque diffuse gray plate which has the emissivity of 0.8. Placed over the opening of furnace and is known to be at 400 Kelvin at a certain instant. The bottom of the furnace, having the same dimension as the plate, is black and operates at 1,000 Kelvin. The side wall of furnaces are well insulated. And the top plate is exposed to the air, having the convection coefficient of 25 watt per meter square Kelvin. The surrounding air is 300 Kelvin here. And we need to find the net radiative heat transfer from the bottom plate. The plate has the mass and specific heat of 2 kg and 900 joule per kg Kelvin. What will be the slope, temperature change with respect to time? So here we have a air as well as the heat transfer from the radiation. So there will be the two modes of heat transfer here, from the convection as well as from the radiation. And in the first part, we need to calculate the heat transfer from the bottom surface due to the radiation itself. So, for that case, this is a rough schematic. This has the temperature of 300 Kelvin. My ambient temperature is also 300 Kelvin. My bottom temperature is 1000 Kelvin. this is a plate having the temperature of 400 Kelvin. So we need to find the heat transfer from the bottom surface. So this is a problem of a parallel plate. So this is a emission from the top one, and the radiosity from the top surface to the bottom one. So these are the radiosity from the side insulated wall. So these are the insulated surfaces, side insulated surfaces. So I am here considering the from the side also, radiosity from the side also. And this is emission from the bottom surface. Now from the charts which I have shown in the previous weeks, that how to find the view factor from the chart as well as from some of the correlation. From these charts, depending upon the dimensions of the system we have given, we can find the view factors such as F12S 0.2, F1S, F1R is 0.8, and from symmetry you can say that F1R is F2R because the radiation from the one is go to, let's say, is go to both the surfaces symmetrically. So this view factor from the top surface is similar to the view factor to both of the sides here, and same will go with the bottom surface also. So my amount of radiation from the bottom surface and from the top surface to this side surface will be the same. So my view factor is F1R will be equal to F2R. So we need to just put all the values into the expression to find but just by calculating this, we will get the heat transfer is 1153 watt. So now we need to calculate the change in temperature of plate with time. So here we need to consider both modes of the heat transfer because we are given the ambient air with a temperature of 300 Kelvin. So we have given a system here, and there will be heat transfer due to radiation and heat transfer due to the convection. So the radiation will there will be the heat loss due to radiation to the surroundings, and there will be some incoming heat due to radiation also. So we can use the energy balance, that energy in minus energy out is equal to the total energy stored. So the incoming energy is due to the radiation, and my total outgoing energy is due to the convection as well as the radiation loss to the surrounding. And my energy stored is given by mcp delta T. So the convection heat transfer is, we know that from the Newton's law of cooling. And we already found the Q rad in the previous previous part of the question. So we just need to substitute here. And when we substitute the values here, we have already given the heat transfer coefficient and the temperatures here. We have given the emissivity, and we already calculated the Q rad, the incoming radiation heat transferred in the previous part of the question. And we have given the specific heat in the question as well as the mass flow rate. And we need to calculate the change of temperature with time. So just putting all the values here, we will get dt by dt. Changing temperature with time is 0.57 Kelvin per second. So in this question, we have two modes of heat transfer. First is convective and the radiative heat transfer, and we use the energy balance to quantify the both mode of heat transfer. So there will be incoming heat transfer from the radiation, and the outgoing heat transfer will be due to the convection as well as the radiation both. So let's move to the last question here. From the last part of the question, we have a two thin aluminum sheet having the emissivity of 0.1. On both sides, it's placed between the two parallel plates that are maintained at a specific temperature and the emissivity. And we need to determine the net rate of heat transfer between the plates. So we have a two large infinite plate, and there is a aluminum sheet which is placed between the two large plates, having the emissivity of 0.1. It's 3.1 and 3.2.1. This is my T1 and my outer is T2. And we need to determine the total heat transfer. So we will be using the standard previous relation here. So we know for the infinite parallel plate, so here I actually distinguish the emissivity of the outer parallel plate as well as the inner parallel plate. So just putting the values here. By calculating this, we will get the heat transfer as 806 watt per meter square. So that's it for today. So for this tutorial, we actually solved the heat transfer relation between two parallel plates. We have solved for different emissivity and different configuration, basically spherical parallel plates and the cylindrical as well as the flat plates. We have solved for the different question, which is change in diameter and change in the emissivity for the two couple of black body surfaces for the gray surfaces. And we found out the heat transfer relation. So for the infinite surfaces, such as infinite cylindrical and infinite spherical surfaces, we have a standard relation to find the heat transfer. And if they are not infinite in case, it is better to use a network diagram to find out the total resistance. So in one of the question, we actually place one plate of lower emissivity, and we then draw the network diagram of that system to find the total resistance. Once we got the total resistance, it is easy to find the heat transfer due to the radiation. And we actually looked the infinite arrangement of the parallel spheres, cylinders, and the plate problems. So yeah, that's it for today. Yeah, thank you.